Thank you very much for coming all the way all around the world. I am one of the co-founders of Topology. I think we also talked, Modulus Labs talked about how they are the first AI on-chain mainnet, but I think one of my co-founders, Guilty Gyoza, he was the first in testnet. I mean, who cares about who's first and who's second or third? I think what's the most important thing is to innovate this place so that we can make more interesting and continue this paradigm shift of verifiable computation. So before we start, I think we want to talk about the importance of experimentation in this space. Starknet, mainnet, and testnet, and verifiable computation, ZK rollup, all of this layer 2s and even above layer 3 and recursive rollups that are going to come about requires a lot of experimentations. I think it's important to embrace what we don't know and also think about admit what we don't know and start working on why we don't know and share this information with the public. Because I think this is an area where we really need to work together to see what's possible. And I think that's the most exciting thing for us to work on Starknet ecosystem and especially on validity rollup. We all know that Ethereum is the world's computer, and I think I don't need to repeat that to this crowd, and we can skip that. And Stark is we saw that the verifiable computation is possible, and what Topology believes that it, and also I think that it's necessary. The next step is to develop a fully on-chain operating system. And I think we'll release a couple of thought pieces in the following week. But I think this presentation, we want to focus on why we're experimenting and what we're experimenting. And maybe you can solve the puzzles and how this is going to evolve into fully on-chain operating system, and also understand what we really mean by fully on-chain operating system, and also why we actually need those. And I will hand over to our collaborators, Greg, who flew all the way from Belgium. He also gave a talk with Guilty Gyoza in Lisbon. So let's give him a round of applause.
Thanks for the introduction. So, as Kunho told you, I'll be talking today about why experimentations matter right now in Starknet. So first of all, in the way we build on chains, there's two ways to do it. So we can either go the bottoms-up way, so like a gardener, or we can go the architect way, which would be top-bottom. So top-bottom is kind of more selling your ideas, building your ideas, and selling those empty ideas to investors, which can be very dangerous because then you end up with difficult implementation. Or you can build primitives on chain starting bottom up, like a gardener. But then it's kind of difficult to find the objective in what you're building and to actually kind of get to channel your energy into one idea. So it's very important to actually combine both these ideas when we're building on chain, when we're experimenting on chain. So at Topology, what we have, an experiment we've been doing is solve to mint, which I'll discuss about it more in a few following slides, but it is opposed to pay to mint, which we see a lot on L1s. The differences on L1s were most focused on just updating mappings, so NFTs are actually just a big ledger you have on chain, and so when you update this ledger by paying a certain amount of ETH, you're paying to mint your NFT. But given the computational power you have on L2s, we can start to assert our identities on L2s by solving puzzles, by proving that we have a certain skill to solve and to mint. So the first solve to min puzzle was just one input that you could put here, which was the initial momentum of the white ball. And the goal was actually to find the value that would give you the most points. So you would get points by having the white ball bounce on colored balls, and it would reset your score to 0 if it ever hit the gray ball. This was all simulated on chain, so it was rigid body simulation with friction collision. And yeah, that was the first experiment we did with solve to mint. We then moved on to solve to min 2, which was more of a puzzle this time. So the goal was to make a closed path starting from anywhere on the board, and you had various rules. So for the circles, you had to go through a circle without turning, but you had to turn before or after the circle. And the square positions, you had to turn on the square, but you couldn't turn before or after. So that was all verified then on chain by a contract to see if your solution was actually valid. And now the new experiment we'll be doing, I'll show you how we iterated on that experiment, and you'll be able to try it yourself to try to get the highest score. It's called Movie. That was the first name we came up with. It's since been changed to Mumu, which was just shorter. Guilty thought that 4 syllables was a bit too long. So we started 3 weeks ago on that one. I hope the video, yeah. So it was a very, very basic game where you can see, so there's what we call mechs, which is the kind of a circle that's moving right now. And it's moving a red circle, which we call the atom. You can give it instructions, which is what are being programmed in the bar. So right now what it's doing, I'll just quickly restart it. It starts at position 3-3. It moves 2 blocks to the right, picks something up, which is the atom, and then moves 2 to the left and drops it down. Since it's starting at position 3-3, it shouldn't pick up anything, and then we actually put it at the position 4-3 to pick up the atom. So here you see it misses the atom. We move it 1 to the right, and then here we'll pick it up. So that was the kind of very, very basic first idea. Then we introduced operators. So operators allow you to combine atoms into a new type of atom, as you see just there. Second step was mech coordination. So this time you see mechs working together to bring the atom from the faucet in the top left to the sink in the bottom right. And so once you have all these ideas together, you can start combining them. So this time you'd have mechs working together to move these atoms from the faucet into operators that allow you to generate new types of atoms. So here's the next iteration we had. This time it brings the atom to the operators, and then the final produced atom is brought to the sink, and you can see it delivered at the sink. Just pause it quickly. Yeah, so we continued on this idea of operators, so we introduced an additional operator, which this time we gave a name to the color of the atom. So the kind of whitish ones were the vanilla atoms, which produce a hazelnut atom. Don't ask me why that was Guilty's choice. And then the hazelnut can combine into a chocolate. You can position the operators yourself, and let's see what all this gives. So here again, you see the mechs working together in a more complex way to produce the output to the sink. And you see the chocolate atom has been delivered to the sink. One second. So up to now we've seen very linear operators where it was just each time 2 input and 1 output, but then now we start to work with an additional operator which takes 3 inputs of 2 different types and produces 2 outputs of 2 different types also. Again, it allows players to have to combine more difficult operation and more complex behavior in the mechs in order to deliver the solution at the end. We've also, I think it's in this video, added the scoring. So you'd get a score based on the cost, on a static cost and on the delivered atom at the end. Static cost being how many mechs you use for your solution and how many operators you use for your solution. Oh. So again here you see all the mechs working together with this more complicated operator. And so let's see today what we have. So that was about 3 weeks work. Again, we try to iterate very quickly. The fastest we go, the fastest we can spot errors, or we can think about new implementations we want to add to our work. And so this is what we have up to today. We've added some visual components in order to actually visualize the atoms. As I said before, we have a scoring that's based on the static cost of your solution, the dynamic cost, which is how many actions each of your mech is performing, and also the average latency, which is how many frames of the simulation you're taking to deliver, well, per atom delivered. We also added a last, more complex operator, which is the smash operator, which will break an atom into, I think, 5 outputs. What's more complicated also with this one is that you actually need to clear out all the output to be able to recreate, to re-input an atom in it. So if you don't clear the output, but you produce the input, nothing's going to happen. So again, we have all the instruction sets for the mechs, and we run the simulation for this setup. You have kind of a resume page with all the score you're getting. And we've also added English, Chinese, and French for the instructions. So this is the current state of all our work. All this sounds very nice, but why did we do all that? It's actually to teach you computer architecture without mentioning computer architecture. So where is computer architecture hidden in all this? So first of all, we can consider the mechs as being separated threads. So they're threads running concurrently, completely independent and interacting through the board, which could be seen as the memory board. You can get data racing, so if a mech tries to pick up an atom on the board, the memory board, but it's not been dropped yet by another mech, then you get a data race. You try to read before writing. And all this allows us to work with coders, or in this case players, to kind of do optimization on the threads, on how the game is running. We also, it's quite an exhaustive list, but we also have some memory allocation, deallocation that needs to be handled by the mech. So, for example, let's say you don't clear the memory board from the output operators, you won't be allowed to produce any more output. So you need to deallocate your playing board or your memory to actually continue playing and to increase the delivered atoms for your solution. So these are the features we've gotten now for season 0, and we're gonna start we're still implementing the ranking, which should be out very quickly, and then everyone can start competing against other coders. We'll rank the players on cost efficiency, as I mentioned, on the throughput, on the latency, to actually rank everyone, and we'll have a very nice ranking page. We're also working on improvements or additional features for season 1, which would be, for example, a private and shared blackboard. Again, if we relate that to computer architecture, you can see it as a mutex lock. This blackboard would allow two mechs to communicate together and say, okay, I've written to the memory board, you can now read from it. So that's kind of a mutex implementation in computer architecture. So as written, we get higher coordination between the mechs. We also want to introduce encapsulation. So that would be, instead of having to write all the time the same instructions for your mech, you can kind of encapsulate functions that you can then reuse. Let's say you want a function that just moves your mech three memory cells to the right and pick up an atom at that position. You can just encapsulate that in a function that you can reuse through all your mechs. That introduces also more modularity. And finally, what we want also for our for Mumu is a richer digital space. So right now we have a certain set of rules that define the world of Mumu, which are the limits of the board, the current operators we have, what actions the mechs can take, but we want to introduce more physics, more rules into the world. We want the players to actually give us feedback on what they think of the game and what they'd want to add to the game. A few quick talks would be like a wall on the board that the mech cannot pass through, or a teleporting hole in the board that allows you to like jump from one cell to another. So that's just a bunch of ideas, but we really want the players to be involved in the implementation and in the ideas with us. So just why are we doing all this, and why are we kind of trying to iterate very quickly on all of our designs? Well, through iteration, we can gain faster and a better design for all of our problems and for our, as Kunho mentioned, our OS. So how do we increase the iteration speed? Well, first of all, if we start to design very big designs, very coupled designs, that will slow down our iteration speed. So if you want to change, or if you've had feedback on your application, but it's coupled to 3 or 4 different smart contracts that you have to rewrite, you're actually slowing down your iteration speed. The next problem would be early promises to your public, to your investors. So being too focused on an idea that you've decided should be implemented for your game, or you've sold for your game, again, you will hurt your iteration speed. And finally are the sunk cost fallacy. So if you've sunk $1 million in your game idea, you feel it's too late to just kind of spin around, which we absolutely do not want to do. We want to iterate quickly, as fast as possible, on our experimentations. Another problem with some of the current implementations we see in the blockchain space is skeuomorphism. So if we take the analogy of the computer gaming and phone gaming, you wouldn't implement CSGO on the phone. You're not going to make an FPS on the phone. You're going to completely change your design patterns once you're implementing a game for a phone. And it's exactly the same for a blockchain game. You don't want to implement I don't know, FPS again on Starknet. You want to change the way you think about your designs, and you want to come up with design specific to the blockchain environment. And finally, what we see a lot also, which can hurt iterations, experimentations, is the imposter syndrome, which a lot of the time is caused by deciding that you want to build a specific idea that you haven't tested, that you haven't brought through stressors or brought through constraints or brought to players, and so you just kind of focus on this idea, this untested idea, which leads you to the imposter syndrome. And blockchain is not just that. Blockchain is still in its very, very early stages, especially on-chain gaming. I think we all believe this, but we also all believe that that experimentation will help it develop, and that going quickly on these iterations will help it move forward. As I said, we're at the very beginning. Ludens from Lattice said we're at the computer renaissance with verifiable computing. I believe it's even more than just blockchain gaming that we're going to change. We're going to change not only the blockchain ideologies we have, but even this very ideas in our society where you can, if you have verifiable computing, you can actually change a lot of domains, a lot of production domains, a lot of coding domains with this very, very great idea from Starknet. So let's explore together, let's think differently, and join us in our experiments.
I think one thing to add over here is to think about what exactly does it mean to put things on chain. And I think by talking about Ethereum, we now have a global computer that is immutable and also that runs feasibly forever. And the games that we thought before were had its own life that is limited. But if you really think about games, I think it's another simulation that we get into. It's a world that we actually lived in there. And the only reason why we couldn't live in that world forever, having another simulation, was because we never really had this computer that lasts forever, that can power this world. And I think now we can just see an inkling of how that can be possible. And I think that's why we are very excited. And also, that's why we focus on experimentation, thinking that when we had a new medium of computation, such as PC or mobile, now we have the world computer that just came about, which is super slow and super costly, and it doesn't really make sense to put this kind of computation on layer 1 because it's super costly for design purposes. And now we are seeing roll-ups and recursive roll-ups. The future that we can think is possible in the far future, and just thinking that we can put whatever the game notions that we had before putting on chain, I don't think that's the future. It's as if thinking like you want to put StarCraft on iPhone. It's never going to work, or Counter-Strike on iPhone. I think what needs to happen is that we need to find what is native on chain. That's why we're having this experimentation of movie, that we can actually have this own limited world where we can have the the interactions that is needed on-chain, and figure out what is needed to innovate in this space. I think that's why we're super excited about this. And also, if you really think about every time when the medium of this so-called virtual world changes from computer to mobile, now we have a world computer, the users of these games changes. From computers, we had like a very long time, like StarCraft or World of Warcraft or League of Legends, where people can play more seriously. Now we have phone, more casual game. And I think for on-chain games or worlds, I think it's gonna change because it's a game that lasts forever. You don't have turns, you don't have rounds, you don't really play with your friend for 3 hours. This is a game that goes on forever, where you can actually have your presence over there, and whatever you buy over there, whatever activities you have over there, is gonna last. And I think the focus over there is about figuring out this coordination problem. Just like in this world that we're living in. You and I live in this world because we think that there's an incentive for us to move forward, get up in the next morning and be excited about it. That's gonna happen the same on-chain and virtually. And this kind of momentum and iteration is something that we've never really seen before. And that's why we at Topology, we strive a lot about experimentation and also really go against the skeuomorphism. We don't want to make StarCraft on-chain. We don't want to make whatever that we knew on-chain because that is not going to happen. We've all seen from DeFi, I think, Spring. Whatever we saw in the financial system that we had before, never really thought, I mean, of course, there are some nuances of here and there where we copied and evolved into, but a lot of mechanisms that are native to Web3 is completely different. And I think this is going to happen the same. Of course, there's limitations on what we can do and how we can power for on-chain worlds that we're singing about. And I think this is the next frontier of blockchain, and I think that's what we are really excited about. And if you are excited about this space, would love to talk to you guys. And thank you for coming over here. Topology, I think we strive a lot about how we can push forward this on-chain computation or verifiable computation. So that's why we are holding these conferences and doing a lot of educational work, holding like an online sessions with bringing other people in to teach people more about online verifiable computation, because the more people we have thinking about this space, the better it is. I don't think this is a finite game that we're playing as I think as a civilization that are trying to put this alternative world that is native to virtually. We all need to play infinite games of where we can actually think what can be possible, iterating and also adding to each other's projects. And I think that's one of the reasons why we said explore genuinely and think differently. And if you want to come join us, please, we'd love to talk to you guys.
Just if you guys want to try the game, it's moo-mu.netlify.app. So
it's moo-netfly or
Netlify.
Netlify. It's always hard to pronounce that. Netlify.app.
Yep.
It's a very, from public's perspective, it's a very boring or can be nerdy, but I think this has a lot of potential and also implications behind what we really classify as a world. And I think it has all the components into it. And hopefully we can iterate a lot and find what is native to on-chain worlds, just like how we found Angry Bird movement for mobile games. So yeah.